there'd be too many yawns and snores by this time, so I'm glad. Okay, so I know this conference is kind of split into, gas turbines and other impacts. This year, they actually brought in impacts of gas for conversions from coal plants. So I'm giving a paper on that, and I'm going to be followed up by someone from the utility, Michael Hale from Southern Company, who's going to be giving a presentation from the utility side. So hopefully we agree on most of the points we're going to discuss. But based on all the reasons you heard today with gas and what's going on, one of the big appeals is you have a coal plant. It's facing a lot of regulation, as Susan talked about earlier. It's facing a lot of competition with gas pricing, as was talked about by other people. And you have a coal plant that is already connected into a grid that can, you don't need any new switchgear or anything. It just needs to have some gas with some minor to major modifications depending on the site in order to become a viable asset for capacity and generation going forward. But there are a lot of things to consider. A lot of people, mostly politicians, like to tout that you just, convert a coal burner to gas, and, it's just as easy as swapping it out, like 1, 2, 3, and then you're done. You're good to go. It's, why not do that? Gas is so cheap. It's so much more friendly, but it's much more complicated than that, and I want to go into some of the details as to what all is involved with that. So I won't spend a lot of time reiterating on stuff that was already spoken about, but some of the main drivers, obviously EPA regulation, natural gas prices, all the shale fracking. This was all talked about earlier. I'm not going to rehash all this, but some things that weren't discussed is natural gas produces a lot less emissions, particularly for your NOx and SOx and mercury, which are all subject to the new regulations. Which is probably the biggest challenge to overcome that we'll go into shortly. So some of the benefits, if you are able to do this, is obviously all the different emissions controls for coal that are listed up here none of them are needed for gas. No scrubber is needed, no SCR is needed, there's no particulate, no baghouses. There's significant advantages to that. Some people think that's obvious, but forget the fact that a lot of the O&M costs associated with coal also get reduced significantly when you convert to gas. Coal handling equipment, ash handling equipment, all those things have a cost associated with it, which you don't necessarily need to worry about when you go to gas. And the big zinger here is based on the new regulations the EPA announced with the CO2 being reduced. We actually have about a couple of studies. We average somewhere around 40% CO2 reduction when you convert a coal gas. Just an example here for 355 megawatt unit we had, you can see it's significantly less, which kind of falls in line with the new EPA regulations on there. Now, granted, that number can change one way or the other depending on the specific unit, but it's a rough order of magnitude so you get an idea. So the biggest challenges obviously are getting gas to the site. And Brian spoke earlier about all the pipeline issues that we have and installing spur lines. Well, from Penn Energy Research, we pulled a data point out that says it's approximately $2 million per mile to run natural gas pipeline to one of these coal facilities. Now, that's an average across the U.S., but obviously it's drastically different if you're running a pipeline on an urban area near Cleveland, Ohio, which is happening right now, actually, or if you're running one out in the middle of the desert out in Utah. So that $2 million is just a national average. It's significantly different based on where that pipeline's actually being run. But as you can imagine, if you're right in that average zone and you're 10, 20 miles away, that's a significant cost. It far exceeds the cost of some of your air quality control equipment to keep your coal viable in some cases. Now, if it's already on site or very close, then it's, a drop in the bucket compared to what some of those other things are. So that's something that, obviously is crucial for any plant that's trying to decide if they need to, evaluate converting to gas or not. And the other thing is regional gas prices versus spot gas prices. You know, a lot of people that don't go into the details, they look at the regular gas price and they say, well, this makes sense here. Why don't we do this? Without actually looking at what gas contracts are available. Is it a firm guarantee, or is it subject to, you know, to move along with the winter? And I go into gas prices a little later just as a quick overview on what can happen with some of those. So when evaluating here, I already talked about the gas price variability, and obviously that's season and region dependent, but there's also a lot of coal price variability. You know, various different sources of coal that you can get are better or worse for emissions, and obviously have higher or lower BTUs and costs associated with it, but it also depends on how far you need to ship it. PRB coal is by far the cheapest coal, but it's only available in one area and still requires quite a bit of finesse in order to make your boiler accommodate that kind of fuel. So it's not necessarily, although it's cheap, it's not necessarily conducive to most. And obviously, when evaluating, you know, there's no scrubbed fuel gas and no coal O&M costs, as I already spoke about. Here's a rough number based on what we've seen of about, you know, 15 or 20 different units that we've looked at. For an actual conversion, here I have 25,000 to 65,000 per megawatt. Obviously, it's a very wide range for an installed cost of converting a unit to coal. Now, this is only inside the fence. It has nothing to do with running the pipeline to the actual site. But what that means is, you know, a 100 megawatt unit, which might be on the pricier end per megawatt side, could range somewhere about 6.5 million for the actual conversion to take place on site, whereas a 500 megawatt unit is much more easy to handle or cost justified because of the duplication required for some of these, and that might, you know, be 500 times that. You have 12.5 million. You know, you have a unit 5 times the size. That's only double the cost based on the size. That being said, a lot of smaller units are the units that are really looking at doing this conversion to sticking around or potentially retiring. Some of the larger units have already invested in those air quality systems or are projected to going forward because of their efficiencies. So I have listed the gas price here from 2002 to 2014, and obviously we're all familiar with the spikes that we had in 2006 and 2009 time frame. And then I have the chart listed out here so you can actually look at it by month going down. So, you know, right around this time frame right here, this is where gas is looking to be real low price for long term. And MATS, the Mercury Air Toxic Standards, also came out about the same time, where coal to gas conversions was the extremely popular idea to go to, because, you know, gas was looking like it'd be so cheap, and in order to meet the MATS rule and avoid bag houses or any type of mercury capture, you know, you just convert to gas. But obviously with the polar vortexes, which were spoken about earlier, there was quite a significant jump recently, and that has a lot of utilities changing their mind on certain things. Not necessarily going away from coal to gas conversions, although some are thinking about it, but keeping the ability to have coal as a viable source going forward, because they don't necessarily trust this gas and what it's going to happen for the next 15 or 20 years. And doing a coal to gas conversion while maintaining coal as a viable option buys you another sort of window for 5 more years or however long you need to determine before you need to actually, you want to install a combined cycle, you want to go back to coal. It'll buy you enough time for a lower cost value in order to determine what you actually want to do going forward with your unit after all these regulations take place and the gas price comes into a little more clarity as far as what it's going to do long term. So from an economic evaluation, and I apologize, it's an extremely busy slide, so I'm only going to highlight a couple of things on it. I have the 5 main coal areas versus natural gas, and you have the price per ton of coal. You can see PRB significantly cheaper than any of the other coals, but again, it has a much lower BTU, much less heat content. So when you factor in what the shipping cost is, which is again heavily dependent upon where you're at, and you factor in what the actual BTU content is and the heat rate you get for each unit, you have a comparative cost right here per megawatt basis. And you can see PRB is still actually significantly cheaper than gas, but gas actually is much cheaper to operate than any of the other coals. Then you factor in the O&M costs associated with that coal handling equipment, which I spoke about earlier. all your ash handling, all your pulverizer maintenance, any of your deliveries. And obviously it's significantly less for gas to give us basically a total evaluation here just for operating of what gas versus these other types of coal are. And again, PRB now, it's still cheaper, but not quite as much. And the highlighted text in red kind of shows here, this is not factoring any large capital expenditures required for any of those AQCS or environmental compliance. So just from an operating cost, you can see coal is cheaper, but when you factor in what's required to meet the environment, as far as bag house, SCR, anything, there's a significant discrepancy with that. And the rest of these are all just the sources that I put in there, which you certainly don't have to read now, but they'll be in the actual presentation for you to look at later and question or disprove or whatever if you prefer. So when it comes to an actual natural gas conversion from coal to gas, you have a lot of things to consider. Again, a lot of people think it's just a burner job. You need to change the burner from handling coal to gas, but it's significantly different from that. And you would equate it to changing your car. If you decided, instead of running gasoline in your car, you wanted to go to something as drastically different as coal is from gas, it would be like changing to wood chips for your car. Obviously, there's going to be extensive modifications needed in order for get your car to work on something drastically different than gasoline and be able to perform at the same speed that you wanted it to. So the first thing is the boiler design is specific to its fuel source. And not just coal, oil, or gas, but even the type of coal, oil, or gas. So the furnace height in the boiler is sized originally on these coal units for whatever kind of coal it was actually going to burn, and the actual entire boiler is designed for that. When you switch it to gas, a couple of things happen that have significant impacts. The main one is the coal flame is very bright and radiant. The gas flame is not nearly as bright and radiant. So inside the furnace, any part of the tubes that sees the flame is going to get much less heat transfer from gas. What that really means is you're going to have troubles making your steam temperature when you go to gas inside the furnace and in your superheat because you're getting much less heat in that specific area. Even though you're throwing in the same amount of BTUs, it continues to act differently as it goes through. Gas, when you get through the actual furnace and into the convection pass, the back end of the boiler, gas has a much heavier weight to the flue gas constituents, which means it can transfer heat better than flue gas can of coal. Now you combine that with the fact that gas doesn't have any ash, which the coal units are designed to accommodate for in the back end, you're now throwing more heat on the back side of the boiler where there's no ash layer covering any of the tubes, and you're starving the boiler for heat in the front side because it doesn't have that bright radiant coal flame. So you have two problems. You have way more temperature than you need on the back side of the boiler, and you don't have nearly enough temperature on the front side of the boiler. So apart from just what you do with the burners, the boiler has to be addressed to handle these sorts of changes in order to accommodate it. So the first thing happens is when you do that, you're going to have a huge efficiency reduction. And I say huge, from 1% is significant for anyone that's operating a coal unit, but we have numbers that somewhere around 3 or 4%, sometimes 5%, and I'll show you those a little bit later. But the second problem is you're going to have trouble with your boiler temperature, your steam temperature. There are a couple of things you can do to address those, which I'll talk about a little later. You also have combustion air issues. You used to have primary air going through your pulverizers to transport your coal, which was used as volume as well as combustion air going through. Now that you're not running any coal, you eliminated 20% of your air, which is volume and oxygen that you were using to combust before that now you don't have, which you have to accommodate for. Some units want to retain co-firing coal capability. They want to make sure, again, what's going to happen with the gas market? I want to have coal just in case, so you have to consider, well, if you want coal to still be available, then it's different from if you want to go all 100% gas. There are also emissions considerations. When you do that, you need to get a permit from the state, and what's the state going to require from a NOx standpoint? Although sulfur and mercury are not really an issue with gas, The NOx is, depending on, you don't need to go to an SCR, but you need to do something in order to get your NOx down. A lot of the RFPs we receive nowadays are in the 0.15, but there are some that are down as 0.08, depending upon what the state requires. And for that, there are things you need to do for it as well. The last thing I'm going to go into, which is kind of a very controversial thing, is the electrical hazards area on code. And code talk is typically very boring. I only have a couple slides on it, but there are a lot of issues concerning what needs to be done when you put gas near a coal unit that has wiring and motor control centers that were not intended to be close to a gas source. Because all those wiring and motor control centers are ignition points close to a gas source. If the gas source was to leak, it's obviously a hazard, and per code, you may or may not have to make any changes. But it's a very confusing code, and I'm just going to go into the brief as to why people are confused and what some people's opinions are. So there's very long text here on this, but I'm going to go through each one of these with pictures to make it a little easier. The first one's very easy. Although your efficiency's down, what do you have to do to keep up? You fire more. Usually the coal units had a spare row of burners, which is very easy to accommodate now. You're going to fire all your burners. You don't need a spare when you're going to gas anymore, so you usually have the ability to add more gas to make up for that lack of efficiency that you're going to get. But the second bullet here is a little harder to do here, and that's the steam temperature. It's very easy to increase your excess air, but you typically don't get a whole lot of extra temperature from it, and it usually doesn't result in getting to the point where you want. You could also add extra surface to your superheater or reheater to get more steam, but that involves changing out very large pressure part components, which can be very expensive, and most utilities want to avoid if they can. The third one is the most common one, and I'll tell you why I'm going to get to the second one. Adding a flue gas recirculation system takes hot gas coming out of the boiler and throws it back into the furnace, where the air temperature going in through was much cooler than it is now when you add gas recirc to it. That helps you get to that steam temperature so your steam turbine can still operate where it's supposed to. The second item here we have for reducing your emissions, there are a couple different burners you can do. A multi-lance burner is the best for wall-fired emissions. That can spread the flame out, but it's a little more expensive as opposed to a solid gun on the inside. You can also add overfired air if it's not already on there in order to try and get that NOx down a little more. And the last one is flue gas recirc again, because you're taking flue gas back in that has much less oxygen than the original air. It's very effective at reducing the NOx. So your two main problems that you have on here are both can be handled by the same thing, which is this flue gas recirc. That being said, that's not the easiest thing to do, because now you need to fit something on the back end of a boiler that has fans, foundations, ductwork on something that wasn't typically designed for it. But in a lot of cases, that's the only way where you can really get to your steam temperature and your emission issues resolved. For your combustion air, when you actually lose your primary air, you need to make some sort of bypass duct in order to take the air you were using to go to your pulverizers and throw it back in so that you don't lose that volume. But that's only a case-by-case basis. Sometimes it's not needed at all, as a lot of times when we found. And then all the other systems, in order to get the gas from inside the fence up to the actual burner front, is fairly significant when you consider each one of them needs pressure reducing stations, flow control valves, and vents in order to go to the top of the boiler roof in order to be in compliance with code. So all those things are a little more expensive than most people realize when they just look at, oh, change the burner out to coal from gas and you're good to go, or from gas to coal, I mean. So I just have 3 examples on here, a couple of different sizes. You have a 130 megawatt unit, 225, and 355. Some are front fired, some are opposed wall fired, and I just list the efficiencies. These are some of the original studies that we did to perform what the actual effects would be if they converted. And the first thing is the efficiency reduction here. It's about 3.5% for the small unit, a little over 4% for the larger units. So because of that actual loss, again, you have to make up for that by firing more. So Oops. There you go. So you can see what happens. In order to maintain your capacity, you have to increase the actual heat input you have. That's the efficiency change in order to make up for it, because you don't want to lose any of that capacity that you have already set up to send out to the grid. You know, you already have your switch yard outside ready to go. To not utilize that, you know, would be a gross waste of whatever your cost justification is for the megawatts available for the project. So when it comes to an actual burner side, what needs to be done, this is a cross-sectional view of a gas-only burner, just to kind of give you an example. And you can see the yellow is a gas spud coming in around. There are typically a bunch of them going right around the face. On a picture, you can see it looks something like this. This is in order to get the best emissions you can, a multi-lance gas burner is the best for it, but it's not that different in order to go from this to change a coal boiler to kind of make it feasible. So what we do, and this is usually our preference, is we take a coal boiler, a coal burner, which is everything in blue that you see, and we add gas lances through the wind box, which is the purple lances that you see, and the tips come right out on the side here. This isn't what we choose to do every case, but it's probably the majority of it. By doing this, there are a couple things that you save. The first is, instead of manufacturing a whole new burner and taking the time to haul it out and put another one back in, you're just manufacturing gas lances, and the only time you're taking is inserting those gas lances through the wind box into the tip. And you almost duplicate that gas design by putting the tips on the outside here, and the coal, which would come down the center here, is completely unimpeded. So by doing this, it's not only a cheaper alternative, but it also doesn't do anything with the coal burner in case you wanted to keep it. So whether you want to keep it or not, it's still usually the recommended method, but if you did want to keep it, coal is still a very viable option on this type of burner with a wall-fired unit. Sometimes that's not an option when you have all sorts of linkage arms on the outside or the face of the wind box, and it's just real congested. So there's an easy solution for that too. You just make one penetration on the outside, bring it into your gas header, which is the blue, and again your gas tips come around the outside just like this. Again, the coal can be brought in still from the center without any issues. So there are multiple different ways that you can provide this to accommodate with whatever kind of burner you have. This kind of just shows you a cross section here where you have the ring header and it cuts in. And then this actually shows a picture of one of the units that we're looking at right now here. So, you know, it's fairly simplistic. You have your gas piping coming, and the performance from a NOx standpoint is almost as good as it is from an actual gas burner, gas-only burner, except now you can run coal with the same thing, and you didn't need to modify the burner as far as pulling it out and pulling it back in. You're just making small, minor modifications. We can do this with T-fired units as well. It's actually easier because most T-fired units have spare compartments that were left there available for oil or other types of fuels to put in. So it's very easy. I'll show you a picture here. These are basically the new gas burners going in a T-fired unit on the front or on the top and the bottom. And you left this open part here where you can see this is the gas header coming in, and it gets brought in on the top and bottom, and the angle, the tilt, is still fully functional, so you can actually adjust in order to get better NOx production out of it. This is just a back view here where you can see here's your two gas spuds burners coming in, and from the outside of the wind box here you can see this is the auxiliary compartment that is available on almost all these T-fired units unless they want to have 3 different fuels where they want to burn coal, oil, and gas, which is very, very rare. This compartment is typically what we'd go to use, and it's actually easier than the wall-fired units. It's just a picture of, you know, what it looks like after when it's actually operating. So Flue Gas Recirc is the next item. This, again, is to take care of your steam temperature as well as your NOx emissions. And it's fairly simplistic in design, but fairly expensive in installation. So when you have your boiler flue gas coming out, instead of going into the air heater, you take a portion off, and you have to put it through a gas recirc fan. This fan has to be controllable to a certain amount so that you can operate it in order to maintain that steam temperature and the NOx emissions. When you're at low load, it should be lower. When you're at high load, it should be higher, and so on and so forth. So after the gas recirc fan, you typically send it into the wind box in some type of mixer, that goes in and blends in with the burners in order to get your lower NOx. That also provides better temperature, and if you need to, you can also provide that flue gas down at the bottom of the boiler in order to get those temperatures up in a lower case. But that's a little more rare. But in any case, this flue gas recirc, it's kind of, solves most of the problems, but it has its own expenses with it. On a smaller unit, this is 100 megawatts. It's kind of hard to see with the black, but this is the actual boiler outlet, and everything in color is the new ductwork here. So this pink is the flue gas coming into the fan, and then it spits out here into the green, which mixes into the wind box, which is in this, this dark blackish color going back in. It doesn't seem so bad here, but remember, this is a 100 megawatt unit. It's one small gas recirc fan, doesn't really need a foundation, can probably put on structural steel, and it's not so bad. But when you look at a 650 megawatt, it's much more crowded here. You need multiple fans. These fans are the type that need full foundations, much more extensive ductwork, but again, it's a 650 megawatt unit. You're getting more bang for your buck. It's just a little more complicated and a little harder to fit in. So from an emissions standpoint, and I put these ranges in here, again, these are pretty loose. This is for wall-fired units only, but actual gas burners by themselves somewhere get between 0.2 and 2.5. If you have over-fired air and they're in a position where you can effectively utilize them, you can get down to the 0.15 area. And obviously, to get down to the real low areas, you need flue gas recirc. And you can get predicted numbers down, extremely low here, 0.06. I think that's the lowest that we have for any of the units that we've actually designed for. We guarantee that at about 0.08. So one of our clients that we looked at had a requirement of 0.15 for two different types of units they had, but then their permit was somewhat in flux, and they actually said, we need an option to get down to 0.08. But it's pretty easy to do. We're still in the design phase, so the flue gas recirc that used was 7% and 10% for each of these units. To get to that 0.08 guaranteed, we just dumped a lot more flue gas back into it. It's, fairly easy to do, but you needed almost double the amount to get down to that number. So it's very easy to achieve very low NOx numbers when you convert these units. It's just a matter of, do you have the room for these large flue gas recirc fans and ductwork, depending on what your number is. And the last one here on these options is, if you have an issue where you don't have enough air because your primary air is being cut out when you in fact demo your pulverizer and your coal system, you can easily create a bypass duct in order to go back into the wind box to try and assist that. Again, fairly simple, but depending on your unit, that might be something that costs just a little bit too much based on your evaluation. These are just the things to consider. So I'm not going to read all these, but I just want to go into the general scope of work with any of these. It involves quite a bit before you actually lay down. All sorts of baseline testing, CFD modeling, and the actual burner modification is just this part. All this other stuff is just in the design phase and what you need to procure in order to meet the requirements. And then there's a second page as well. And this is all the other stuff that's needed. So again, it's not just a burner change-out issue. All this stuff is required in order to make sure your boiler is going to perform for your steam turbine with your megawatts in order to get where you need to go. And this just shows you an example, even from a gas piping standpoint, it's fairly well, it's not just running one pipe from the fence all the way up to the boiler. There are lots of pressure reducing stations. You need to keep reducing it down, diverting between multiple units at the same site in many cases. And once you get up to the actual burner deck, you have several valve stations like this in order to control the actual gas flow to each burner. So again, the three largest scope items are all the flue gas recirc, if it's needed, the ductwork, the fans, the foundations, running all the gas piping, and then the smallest of those three is actually that burner modification, which is usually what the only thing people think about up front. It's just a diagram showing you, what it looks like for the gas piping and how detailed it is. So the last thing I wanted to talk about is really the stickiest situation here, and that's the NFPA code. And I am by no means a code expert, but there's a guy that works for my company who is, and he taught me, whatever he could in a 15-minute lecture to go over it. Basically, if you're introducing gas into a place where it did not exist before, and there are electrical components that can create a spark. There are 3 different sections of the code that address it. Unfortunately, they don't all agree with each other. The first one here is the extent of a classified area is 15 feet from any point of discharge. Point of discharge means where you could have a potential gas leak, which is just about anywhere on the gas pipe. So if you're running this gas pipeline, you know, a quarter of a mile, you need to measure 15 feet from any of this leak to look for any potential ignition sources. And from this standpoint, it seems pretty clear cut and dry. You need 15 feet area in order to make sure you're in compliance. Now, any of those spark sources can be upgraded to be explosion proof or rated within code, but that's very expensive on some of these old units where you have wiring, you know, from 50 years ago that's still sitting there that you don't really want to touch. So at least from this, from the NFPA 70 NEC code here, it sounds like you have to do it, but there's some contentions here. When you look at NFPA 85, NFPA 85 says all equipment shall conform with the National Electric Code. Okay, that's fine, but then there's an asterisk. When you look at the asterisk, it says locations, and I won't read the whole thing, but basically it says normally not considered hazardous locations. So this one basically says if it's already there and there's a boiler present, you don't really need to worry about it. It's not considered hazardous. But the title of the chapter, it says only applicable to single burner boilers. So some people take this sentence here and say, well, it says I don't need to do it. I don't necessarily know if they really meant to say that, so I'm going to go with it because it's a little dicey. The 3rd section of the code, which is NFPA 497, reads pretty clear cut here, open flames associated with the equipment such as boilers and fired heaters that are inherent thermal ignition sources, meaning a boiler is designed to take fire, it's designed to operate in this way. It says electrical classification is not appropriate in the immediate vicinities, which means there's your get out of jail free card. I don't need to do it at all. It's very clear, very cut and dry, unlike the other 2. And then you read the next sentence. However, it's prudent to avoid installing electrical equipment that could be a primary ignition source. Well, what the heck does that mean? It means I can't do it, but, well, you don't have to do it, but it would be very prudent to. So there are various opinions on this subject. And to be honest, as one of the OEM vendors, we really don't want to get involved with it. We want the utility to decide what is best for the utility to do in order to be in compliance. And I'd be lying if I told you everyone said it has to be done and we're going to follow the code from the conservative approach. We've seen RFPs from both stances where they say, we just want you to replace what's there, don't worry about anything else. We've seen stances that say, please make sure you put a proposal in to change out everything within 15 feet of the natural gas pipes that are coming in. And we've seen other proposals, which is our least favorite, which say, why don't you determine what's needed and tell us what to do? And I can tell you, in every case where we get that, we are going to take the ultimate conservative approach because we do not want to take any chances with any code violations or, more importantly, any accidents that could occur based on providing equipment in an area that could or could not be a hazardous location. So that being said, I'm not a code expert, but I'm smart enough to know that that confuses the crap out of me, and I don't want to touch it. That being said, that's the last slide I have, and I'll still take any questions. Anyone?
Anyone have